The Department of Energy is in the process of destroying America's supply of uranium-233, an extremely rare uranium isotope not found in nature. Hundreds of millions of dollars are being spent to downblend and vitrify it. Today, this act of destruction is costing American taxpayers $500 million. In the future, the cost of this destruction will be described in billions, if not trillions of dollars, as the full impact of this plays out. To understand what is at stake, we must first familiarize ourselves with three elements on the periodic table: uranium, plutonium, and thorium. All of these elements are found in nature, but only the tiniest amounts of plutonium exist naturally. Almost all of plutonium is man-made. You're probably familiar with plutonium's use in nuclear weapons, but it is also used in NASA space probes. The natural decay of plutonium releases energy, which is needed by any space probe traveling beyond the asteroid belt as the sun's rays become too diffuse to provide power. The instrument created by NASA to harness plutonium's decay energy is called an RTG, the Radioisotopic Thermoelectric Generator. All of the following spacecraft were powered by RTGs.
Pioneer streaks away at 1 million miles a day.
The Pioneer 10 and 11 spacecraft both had 4 RTGs. They were the first spacecraft to Jupiter and Saturn.
It was left to Voyager 2 today to get the first close-up pictures of Europa, where we see things that are only a few kilometers across.
The famous Voyager spacecraft each had 3 RTGs.
On December the 7th, 1995, Galileo dropped a probe that fell into Jupiter's atmosphere at 260,000 kilometers per hour. It gave scientists a glimpse of Jupiter's interior.
The Galileo spacecraft had 2 larger and more modern RTGs.
Since its arrival around Saturn in July 2004, the Cassini-Huygens mission has opened new vistas on the ringed planet, its myriad of satellites, and the prime focus, Titan, its largest moon.
The highlight of the year is really the Huygens landing on the 14th of January 2005.
The in-situ sampling of the atmosphere confirmed a rich organic chemistry. Results from several instruments imply that Titan must periodically have methane showers, with a phase cycle much like that of water on Earth.
The Cassini spacecraft had 3 of these larger RTGs.
And even the latest Mars rover, Curiosity, is powered by RTG.
Curiosity is 2 times bigger, 5 times heavier, and has 15 times the weight of scientific equipment relative to Spirit and Opportunity.
Hi, I'm Ashwin Vasavada, the Deputy Project Scientist for the Mars Science Laboratory mission and its Curiosity rover. So a lot of people wonder why Curiosity doesn't have solar panels like the Mars Exploration rover, Spirit and Opportunity. Collecting samples of rocks and soils with a big jackhammer drill located on the end of a 6-foot robotic arm. Those samples are delivered to the rover and analyzed with some very sophisticated and power-hungry analytical laboratory instruments.
This plutonium allows Curiosity to operate in winter.
The Mars Exploration rovers often found themselves short on power as dust settled on their solar panels.
They were the only source of energy, and the Martian winter was approaching.
The part of it that really breaks my heart is that we were making progress. We just needed a little more time and we would have done it, and we just didn't have power to drive anymore.
Winter nights on Mars can freeze to around 100 degrees below zero, enough to kill circuits and electronics for good. Spirit has remained at her final resting place next to the home plate plateau, a hard-fought 8 kilometers from her landing site on the far side of the Columbia Hills.
More research is being conducted on Mars today because Curiosity is powered by plutonium. The plutonium found in any NASA RTG is one of many possible plutonium isotopes. Here are 2 of the many possible isotopes: plutonium-239, used in bombs, and plutonium-238, used in NASA's RTGs. All 3 of the elements we are discussing, uranium, plutonium, and thorium, have many isotopes, and each isotope has different uses. The uses of uranium-233 are many. They include powering America with an inexhaustible supply of clean, inexpensive energy. They include fighting cancer with new radioactive medical isotopes. And they include the continuation of America's deep space exploration. You want a clean future where America ends its dependence on oil imports from the Middle East? Then do not spend $500 million to destroy the uranium-233. You want to fight leukemia, cancers of the pancreas, kidneys, and other organs with new targeted alpha radiotherapy techniques? Then do not spend $500 million to destroy the uranium-233. You want to continue sending probes beyond the asteroid belt as we've done in the past? Then save yourself $500 million and halt the destruction of uranium-233. Now, uranium-233 does not accomplish all of these tasks itself. There's not enough to use it as a nuclear fuel the way today's reactors consume natural uranium isotopes. There's no alpha radiotherapy technique where uranium-233 is injected into anyone's body, and NASA probes do not contain uranium-233. But what uranium-233 can do, which is unique, which is why it is an invaluable resource, not just to the United States, but to the world, is that it can be used to inexpensively create other rare radioactive isotopes.
Gallbladder function, or kidney scan, or blood pool imaging. Each one of these is a compound that the molybdenum is connected to in order to do that. Right now, it's made in just a handful of research reactors that are scheduled to be shut down. There's some great papers written about the market failure of not having the money that's being made in technetium going back to operating these reactors.
This can be accomplished as a free byproduct of producing civilian energy using a molten salt reactor, often abbreviated to MSR. You may have already heard of LFTR, LFTR, the liquid fluoride thorium reactor. LFTR is one specific molten salt reactor design. Due to video footage constraints, we'll have to use MSR and LFTR interchangeably in this video. In LFTR, the uranium-233 acts as a nuclear catalyst, facilitating the consumption of thorium as fuel.
Through this process, if you had some uranium-233, you could catalyze the burning of thorium indefinitely. You're fissioning uranium-233, but you're making a new one. So it's not really a catalyst in the true chemical sense that a catalyst is not consumed in a reaction, but you can almost think about it as a pseudo-catalyst.
As thorium is converted into energy, radioactive isotopes are created. Some of these isotopes are similar to those produced in today's reactors. Some are quite different.
General idea is you don't want uranium or thorium or anything else to end up in your waste stream, and that's a pretty straightforward proposition in this fluid-fueled reactor. So our waste story is a lot different. Making less of it, moving towards stability much more quickly. You can also then take some of the waste that's already been created in our uranium-fueled reactors and potentially destroy those long-lived transuranics through fission. You know, waiting them out to decay is a very slow process. Plutonium-239, for instance, has a 24,000-year half-life, so that's a long time you're going to be waiting for that to decay.
Molten salt reactors can be designed to facilitate isotope isolation and extraction.
Victor didn't like solid fuel. He was a chemical engineer by training, and he thought, what kind of industrial process do we run chemically based on solids? He goes, we don't. Everything we do, we use as liquids or gases because we can mix them completely. You can take a liquid, you can fully mix it. You can take a gas, you can fully mix it. You can't take a solid and fully mix it unless you turn it into a liquid or a gas.
All of these industrial processes, they're radiation hard. They don't require the fuel to be aged or stored for some period of time, and that's a real contrast with how people talk about doing existing nuclear fuel processing today.
We get clean energy, we get isotopes, all from thorium. The United States already has a 3,000-ton stockpile of thorium buried in the Nevada desert. Thorium is also a waste byproduct when monazite deposits are being mined for heavy rare earths. Thorium is extremely plentiful stuff, and it is very easy to isolate from other elements.
Almost every known way to extract rare earths from their mineral concentrates means that thorium just literally drops out like a rock and you have it.
It's good to go. There's no such thing as highly enriched thorium. It is what it is right out of the ground.
A single cubic meter of regular Earth, anywhere on the planet, it will contain roughly 2 cubic centimeters of thorium metal. So if you could extract all the thorium from a regular piece of dirt anywhere, you'd get about 2 cubic centimeters of thorium and about half a cubic centimeter of uranium. If you were to consume that thorium at high efficiency, it would be as if that cubic meter of Earth had the energy content of 30 cubic meters of crude oil. But the key is to build a machine that has the ability to very efficiently convert thorium into energy. thorium-232. When it absorbs a neutron, becomes uranium-233. That'll fission 90% of the time. So only 10% of it makes it to become U-234. 1.5% could potentially make it to neptunium-237, which is your first transuranic. That then can be physically extracted from the salt if desired, and you've arrested the formation of further transuranics. Or an alternative would be to retain it in the salt and form plutonium-238, which at NASA we are just really, really dying to get our hands on.
The molten salt reactor is radically different from today's nuclear reactors. This is because today's reactors answer the question of how to power a 1950s nuclear submarine, and not the question of how do we wean mankind off fossil fuels as quickly as possible. World War II, the Cold War, and Nixonian politics are all reflected in today's nuclear reactors.
But I am being ruthless on one thing. Any activities that we possibly can should be placed in Southern California. On the committee, every time you have a chance, needle them, say, where's this going to be? Let's push the California thing. You do that?
I am so delighted you released that $16 million on the enriching complex.
Good.
That handles a bad blood problem for us.
Right, good.
Nixon was from California. Hosmer was from Southern California. Holofield, Chet Holofield, who ran the Joint Committee on Atomic Energy, was also from California. Testimony given in September of 1972, they noted that the U.S. government would be expected to cover cost overruns on the breeder reactor, and the development cost would go over $700 million. At this point, industry had already committed $200 million, these are then-year dollars, to the breeder reactor effort. Representative Craig Hosmer, who was the fellow on the phone call that we heard earlier, said that if cost targets were missed, I, for one, don't intend to scream and holler about it. In that same month, the Atomic Energy Commission issued WASH 1222, which was an evaluation of Weinberg's molten salt breeder reactor. It almost completely ignored the safety and economic improvements possible through the use of the molten salt breeder reactor technology. In January of 1973, Oak Ridge was directed by the Atomic Energy Commission to terminate the development of the molten salt reactor. So they put all their chips on the fast breeder reactor, and that didn't work out too well for them. They'd even actually built one in Monroe, Michigan. It had had a meltdown. And nobody, as far as we know, in D.C. ever revisited the question of was it a mistake to cancel the molten salt reactor effort? Should we have gone back and said, you know, now that we're not going to do the fast breeder, maybe we should have done the molten salt breeder reactor?
Today's reactors are typically fueled with a mix of uranium isotope oxides in solid form, wrapped in a coating of zirconium alloy. These solid fuel rods are built to survive inside a reactor as long as possible.
Any nuclear fission is going to make gaseous fission products, xenon and krypton. As gases, they have a huge amount of volume per unit mass. And that leads to cracks and distortions and swelling in the fuel. When the fuel swells to a certain point, the clad can't hold it anymore. And when the clad can't hold it anymore, it's time to remove the fuel from the reactor. At this point, only a small amount of the energy has been consumed.
We can't consume all of the uranium fuel in today's reactors because the lifespan of fuel rods will not allow it. They become contaminated with a great number of radioactive isotopes, both which impedes their performance and leads to a spiraling creation of even more isotopes. Now, as you already know, many of these isotopes are extremely useful. Some could save lives if only they were not trapped in a zirconium alloy-coated solid fuel rod.
You can take a liquid, you can fully mix it. You can take a gas, you can fully mix it. You can't take a solid and fully mix it unless you turn it into a liquid or a gas.
To put those isotopes to use, the solid fuel rods would first need to be converted into a liquid.
After chopping the fuel rods into small pieces, you submerge them in a vat of molten salts. When you run an electric current through the vat, the uranium and transuranics separate out and forms crystals on the electrodes.
Because it is so expensive to do this, and because no one wants to cart spent fuel rods across the country to a reprocessing site, America's spent fuel rods instead sit in cooling pools in the same reactors which created them. These rods can be considered either nuclear waste or nuclear fuel, depending on your optimism that they will be reprocessed. Regardless, many of our reactors are running out of space for additional spent fuel rods. At Fukushima, the proximity of spent fuel rods complicated the challenge of cooling the overheating reactor when cooling pumps stopped. Today's reactors also use water to transfer heat.
The oxygen has a covalent bond with two hydrogens. Well, neither one of those bonds is strong enough to survive getting smacked around by a gamma or a neutron. They're just going too fast. And sure enough, they knock the hydrogens clean off. Okay, well, here's what happened in Fukushima Daiichi. They ducted the hydrogen up to the upper decks of the reactor, which were outside of the containment. There's just kind of a sparse steel frame structure up there. And 1, 2, 3, we saw it happen on the news. Filled with hydrogen, got to a certain point, boom. Let me diss on water a few more times.
At normal pressures, water will boil at 100 degrees Celsius. This isn't nearly hot enough to generate electricity effectively. So water-cooled reactors have to run at much higher pressures than atmospheric pressure. And this means that you have to build a water-cooled reactor as a pressure vessel with steel walls over 20 centimeters thick.
The number one accident people worry about with this kind of reactor is what's called a double-ended pipe break. One of these 8 pipes, for whatever reason, shears. And all of a sudden, pressure is lost in the reactor. Flashes to steam. Its volume increases roughly by a factor of 1,000. You get this entire containment vessel filled with water. Now, I don't want to tell you all this because I'm trying to focus on negative situations here. I'm telling you this because this is what drives the design of this building. This building is the size it is, and it's the way it is, precisely to accommodate this event. They've designed this reactor so if this happens, all of the steam is captured in this building and doesn't get out. Look at the size of the reactor. Look at the size of the containment building. It's huge. And that's all driven by that 1,000-to-1 difference in the density between steam and liquid water.
In fact, the temperature differential between cool stream water and hot pressurized reactor water only achieves a 33% thermal electric power conversion efficiency.
All our reactors today use steam turbines.
They're based on boiling water, running a steam turbine, and then condensing that water. That's why we have big cooling towers. That's why we have to place our reactors by rivers or lakes, is because we use this steam turbine power conversion system. Now, we don't use that because we're stupid. We use it because the limitations of pressurized water mean that you can't get it all that hot. I mean, the reactor just doesn't get that hot. It gets to about 300 C, which is modestly hot, but not all that hot. And the steam turbine's the best fit for those temperatures. With this reactor, we can get up to more like 700 or 800 C.
From the potential of mined uranium ore, today's reactors are less than 1% efficient.
Nuclear has the advantage that the amount of energy sort of per atom is about a million times better than coal or natural gas. So you start with this huge advantage, and yet the complexity of the plant, you more than wipe out your million-for-one advantage, and today's nuclear plants are fairly expensive. Nuclear innovation stopped in the 1970s. We basically have this sub-design thing that was put into Shippingport for the first power generator, and we basically built 400 of those.
We're extracting about 0.5% of the energy that's in the uranium. You can imagine going to your boss saying, I developed a new system. Well, how efficient is it? It's less than 1%. Excuse me, what did you build? I think you need to go work on that again. I mean, we just simply wouldn't accept this.
By improving efficiency, we aren't just creating more electricity, we're generating less waste. From depleted uranium to spent fuel rods to waste heat being released back into streams, there is ample room for improvement.
And I'm very impressed with how the nuclear industry has operated safely for so long. But it comes with great complexity, great carefulness, and great cost. And if we want to move into a world where nuclear is far more prevalent, safer, and cheaper, we've got to change these fundamental principles, and we've got to move away from high-pressure operation.
With molten salt reactors, we start by doing away with fuel rods, instead dissolving the thorium fuel and uranium-233 catalyst into a molten fluoride salt. The salt can't melt in an accident because it is already melted, and won't boil until well above 1,000 degrees Celsius. Neutron bombardment will not disassociate the salt at all, let alone into explosive gases. This is a safe, stable way to contain our nuclear fuel. Molten salt reactors operate at ambient pressure because we don't need pressure to keep the liquid salts from boiling, so there is no risk of rapid phase change. With molten salt reactors, any accident, any incident, anything that can possibly go wrong, ultimately results in liquid salts melting through frozen salt plugs into a drain tank under the reactor. There, the salt is passively cooled over a large surface area. Whether the salts are hot liquid or cool solid, They continue to trap radioactive isotopes inside. The fuel can't burn, and so the fuel can't send isotopes into the atmosphere as smoke or steam. Molten salt reactor fuel can be reprocessed continually. Valuable isotopes can be extracted as they are created. In some cases, this is necessary, as they may have very short half-lives.
For over 50 years, we've been focused on the electricity that can be generated from fission, but about 5% of fission leads to the formation of the molybdenum-99, the 99 mass decay chain. And it could be that this is potentially worth even more than electricity. What's unique about LFTR is that we can extract this valuable product while making electrical power. We can do both at the same time. Our power reactors today, they make lots and lots of molybdenum, but it's not extractable. If you want to get it out, you'd have to shut the reactor down, depressurize it, cool it, extract the fuel, reprocess it. By the time you did that, the molybdenum's all gone. It's only got a 66-hour half-life, so you can't do it fast enough.
Alvin Weinberg drove molten salt reactor research as director of Oak Ridge National Labs in the 50s and 60s. He once complained that the molten salt approach has too chemical a flavor to be fully appreciated by non-chemists. Possibly he was observing that physicists dominated development of civilian nuclear power in the 1960s, and concerns such as fuel reprocessing were not being considered from a practical perspective.
In addition to being a thorium guru, Weinberg was also the original inventor of the pressurized water reactor. He had invented it and gotten his patent for it in 1947. So it was a little bit of a tricky thing to have the inventor of the light water reactor advocating for something very, very, very different. There was a congressional leader named Chet Holofield,
a member of the Joint Congressional Atomic Energy Committee,
who told Alvin Weinberg, he said,
Alvin, if you're so concerned about the safety of reactors, then I think it might be time for you to leave nuclear energy.
And Weinberg was really kind of horrified that they would have this response to him, because he wasn't questioning the value or the importance of nuclear energy. If anything, he was far more convinced about that than anyone else. What he was questioning whether had the right path been taken in the development of nuclear reactors. And he was particularly well suited to make that question because of his role as the inventor of the predominant technology. So he was quietly shown the door. It just burns me up, because I think big mistake the United States made in 1972 in walking away from this.
In 1974, Alvin wrote about the global effects of man's production of energy, and in 1975 testified before Congress on the dangers of global warming. America's uranium-233 combined with plentiful thorium provide an answer to both our domestic energy challenges and to the threat of global warming. They can be deployed on ocean coastline, providing enough energy to desalinate seawater as a free byproduct of energy production. With uranium-233, every one of these reactors could be producing valuable medical isotopes and fuel for space missions. Depending on how they are configured, they could even produce more uranium-233 for use in future reactors.
We have world population growing from 6 to 9 billion people. On the left, you see income measured in GDP per capita and the numbers of children per woman. Those countries with the highest birth rates have the worst poverty. On the left-hand side, the red line, which is about 2.3 births per woman, you see the stable or decreasing populations in countries in the world. On the right, increasing. If we could bring countries to that level of prosperity, we might begin to solve our population problem. Prosperity is related to energy. If we can bring people to about 2,000 kilowatt hours per year of electrical energy, they have a chance at achieving prosperity. Heat, light, transportation, safety, and so on is an important, critical element of prosperity today. Developing countries know this.
In fact, if you could pick just one thing to lower the price of to reduce poverty, by far you would pick energy.
Energy and coal use is growing rapidly in all the developing countries. They want to achieve that level of prosperity, and they're being supported by Peabody Coal. If we can provide an energy source cheaper than from coal, all the nations, in their own economic self-interest, will choose it over coal. Coal costs about $40 a ton in the U.S. today, 2 cents a kilowatt hour just for the coal fuel. So this says electricity is about 5 cents a kilowatt hour. In the LFTR case, we're looking at a little less capital cost than a coal plant. The cost recovery then 2 cents a kilowatt hour. the fuel cost being negligible, or a total cost of about 3 cents a kilowatt hour.
Rich countries can afford to overpay for things. We can afford to overpay for medicine, we can overpay for energy. In the world where most people live, 80%, energy is going to be bought where it's economic so that they can buy cheap fertilizer and grow enough crops to feed themselves, which would be increasingly difficult with climate change effects that they're experiencing. And for the CO2 problem, even if the rich world did very dramatic things, it doesn't come anywhere near to solving the problem. You have to help the rest of the world get energy at a reasonable price in order to have gotten anywhere.
This is where I have a differing opinion than I think a lot of environmentalists. They're always trying to drive us towards using less energy because all that energy is coming from the consumption of fossil fuel. Well, let's say your energy is not coming from the consumption of fossil fuel. Then you could use more energy, and you could use more energy to accomplish things that you are not able to do right now. Break up carbon dioxide, dissociate water, make fertilizer, grow crops, all that.
So much energy, an abundance of energy, that it would drive the price down to the point where the only oil we'd be taking out of the ground would be the easy to get to oil, and there's not going to be any more environmental devastation than there already is.
If we didn't have to worry about energy, we could think of so many more things to do.
If there was a lot of it, and it was cheap, and it was not harmful to the environment, what would you do that you're not doing now?
We might try to synthesize fuel. You can configure it not to produce electricity, but to dissociate water. You can make ammonia out of hydrogen, which can be a fuel. It's also a fertilizer. Ammonia production that consumes more than 1% of the entire world energy budget today. You need carbon in order to make these. The Sandia project, Green Energy, they figure we can get carbon out of the atmosphere and manufacture gasoline for about $4 a gallon.
If you're near a coastal body, you can take seawater in and you can desalinate it. Well, why aren't we desalinating seawater today? Well, some places we are, but usually it's because it's really expensive. We're burning fossil fuels, desalinate seawater. That's not a good idea. In this case, almost no economic penalty to desalinate seawater.
This is a future of energy abundance because our energy can be produced without pollution. Today's nuclear power has already contributed to our energy independence and helped reduce the amount of CO2 we've put in the atmosphere. But we need safer, cheaper, more efficient reactors to expand on this. To destroy our uranium-233 stockpile is to severely limit the capability of our future nuclear fleet and the economic potential of our great nation. Thorium advocates have tried contacting the Department of Energy on this matter. This is a very typical response. DOE lists off the different types of reactor research they are conducting, but at this time, we are not conducting any work specifically related to molten salt reactors. Thorium enthusiasts are aware of other proposed future nuclear plant designs. They all use solid fuels and therefore cannot achieve the same level of efficiency molten salt reactors can. This is like optimizing a coal-fired automobile to run more efficiently on coal. Maybe what's needed here is a liquid, homogeneous fuel instead. The storage of special nuclear material requires a significant effort and funding to ensure the security of the material and the protection of the public. Under our current budget, the Office of Nuclear Energy cannot take ownership of this material for what would be an indefinite period of time. We are currently not supporting any projects that require uranium-233 for testing. As such, the disposal of uranium-233 will go forward as the schedule and funding of EM allows.
There are currently about 300 people working full-time on it. There are about another 100 people from our side to work on it, so a total about 400 people.
So even though China Academy of Sciences is pursuing molten salt reactors right now, even though startups in the United States are actively designing molten salt reactors right now, even though this uranium-233 represents one critical asset in molten salt reactor development no other country on Earth possesses, they're going ahead.
For the liquid-fueled molten salt reactor, we're seriously thinking doing the conversion from thorium to uranium-233.
What kind of fissile material do you expect to start up these molten salt reactors?
Uranium-235.
Is that true for both the cooled and the fueled reactor, or just the cooled one?
Just the cooled one.
What are you planning to use for the fueled one?
That we haven't decided.
Well, if you need any U-233 to start up the molten salt reactor, we have some that you can talk to DOE, your DOE friends.
Well, that's good to know.
Because we're planning to waste $500 million on destroying it.
When is our stockpile scheduled for decommission?
The uranium-233, it's the decommissioning is undergoing as we speak. So this is something that we need to act on soon.
Public interest in thorium as an energy resource only began in 2009 with a feature story in Wired magazine. The very first molten salt reactor-based startup was only founded in 2011. We need to stop and think about this.
That U-233 sits right in the middle of the Oak Ridge campus, and they want that land back. And why they can't just pick it up and move it over to Y-12, I'll never know. Why this is such a arduous thing. Maybe there's all sorts of technical stuff, but not $200+ million worth of technical stuff. One way or another, we've got to save the U-233 because that is the patrimony of the United States. To reproduce that stockpile of the U-233 would cost billions of dollars and probably never able to be reproduced. And that is the one advantage we have in the world in terms of who's going to develop the molten salt reactor based on thorium. Well, that is the one keystone element that we have over every country on the face of the planet. Everybody else would have to use U-235 or some sort of electron beam called the accelerator-driven system. Every other way is not as good as using U-233, and we're about to destroy it. So, if you care, we could all write senators together and beg and cry on their doorsteps not to waste a couple $100 million of America's money to destroy our future.
Just a thought.
We are not asking for government money. All we want is for the destruction of our uranium-233 to stop. It was created with taxpayer money. It belongs to the citizens of the United States. Thank you for watching. Please take one more minute to sign the thorium petition.